Physics Lab 1 on constant velocity. Some of the key topics that we'll be covering through this demo include the physics concept involved, the tracker demo followed by some of its results, the model demo followed by some of its results, especially overlaying the results of the observations with the results from tracker. Next, we'll also look into the results in the negative x plane and discuss some of those outcomes, followed by which we'll finally look at the results overall in terms of the forces involved, and we look at some possible improvements. In terms of the physics concepts involved, the main one is Newton's second law. We know that the force acting in this case will be zero because we're moving with a constant velocity, hence F net is zero. Another way to also look at it is because in this case, since the mass is constant and F net is zero, we know that our acceleration will be zero. Furthermore, since we're moving at constant velocity, we know that our velocity isn't changing with respect to time, due to which the acceleration is also zero. Next, in terms of the update of velocity and position, we know that because acceleration is zero, these two terms cancel out. The result is that the initial velocity equals the final velocity, and the final position equals the initial position plus the initial velocity times time. These are the formulas we'll be using in our model. In terms of the tracker demo, here we can see the pool ball moving across the pool table. As you can see, tracker takes account for each of the different positions through time, and it makes a model out of it based off the position and time graph and the velocity in the x component versus time as well. We don't need to consider the y component because the ball isn't really moving much in the y component. Some important key observations there is to use both the axes and set it to 0, 0, which is the center of the ball. That's important to make sure that the ball starts in the 0, 0 position. It's also important to put a point mass all around the ball to make sure that the edges are considered accurately. And lastly, it's important to calibrate the distances. I, in this case, use the diameter of the pool ball being 0.055 meters to calibrate distances accurately. In terms of some of the results, you can see that the velocity is more or less constant because the slope of this position time graph is constant, and you can see that it really doesn't vary very much. And it's kind of constant in between a small interval. In terms of the demo, it's important to make sure that a few conditions are set correctly. We need to make sure that the initial position of the ball is that which is observed in tracker. As you can see, this is where tracker starts. Another important observation is that we need to calculate the average velocity of the ball during its motion in order to make sure that the model is moving at the correct velocity. I've used a spreadsheet to do this, which takes the average of all the different velocities using tracker. And lastly, I have made sure to set that to the initial velocity of the ball. Moving on, it's also important to consider that the average velocity was used as the initial velocity, as I mentioned earlier. We're not really taking mass into account, although I have set it, but in this case, since F net is 0, it doesn't really matter because there's no acceleration. It's also important to make sure that I add a constant velocity of 0, 0, 0 to make sure that the initial is equal to the final velocity, and this is this line over here. And lastly, for the position update, it's important to make sure that the final position, as I mentioned earlier, is equal to the initial plus average velocity times time. In this case, the time is 0.033 seconds, which is the frame rate in tracker. And as you can see, I have made that update over here. This number over here represents the velocity times the time, which is being added to the position. The velocity being this position, the time being t delta. As you can see, when I run this program, the model works properly and it moves through that small distance in the correct amount of time, and the velocity remains constant. This is identical to what we observed on tracker. Some of our key results overlaying the two graphs, you can see that the variation isn't too much, and that's because our experimental setup doesn't have too much external forces. As you can see, they're relatively similar. When considering a negative x plane, it's important to understand that we're moving in the opposite direction. In this case, we're moving in the negative x direction. As a result, it's important, two key observations are that the magnitude of the velocity actually remains the same, but the velocity vector, because we're moving in the negative x direction, will also be negative. As a result, you can see that the velocity values are negative because we're moving inside the opposite direction. Some final conclusions to consider are that in our case, the force acting is actually 0 because in our model there are only two main forces, that of gravity, which pulls the ball downwards, and the normal force, which is equal and opposite to it. As you can see, this diagram shows these two forces pretty accurately. In real life, there would also be this resistive force, which in this case is friction acting in the opposite direction to motion. But we won't be considering this in our case because we are assuming in our model as well that there is no friction, we're moving on a frictionless surface. Lastly, some improvements to consider. We could use a smoother surface to roll the ball over, as that would reduce friction. We could also reduce the glare, which is affecting some of the results on Tracker by making sure we adjust the lighting conditions appropriately. And one last one would be to take multiple videos and launch the ball with the same force and then average out the results to reduce the total systematic error in the system.